All right, today's lesson, we're going to talk about the chain rule. So this is how you take the derivative of a composite function. So something that's in the form of f of g of x. Okay, you could even have more functions inside, like f of g of h of k of x. Okay, and just you kind of peel it like an onion, and you work your way from the outside in. All right, so a composite function, some examples. So f of x is given to you as x to the seventh power. G of x is given to you as 3x squared plus 5. So f of g of x would be taking 3x squared plus 5 and plugging it in for x right there. So you have 3x squared plus 5 where x used to be, and then to the seventh power because that was the function there. All right, so same deal for these two examples. They x cubed plugging into sine would be sine of x cubed, and then cosine of x plugging in for x right there would be cosine of x cubed, and then we usually write that as this. Okay, I want to be clear that these notations are not the same, so this does not equal cosine of x cubed like that. If you write it like that, we will assume, people reading your work will assume you meant x cubed, and that's not what you meant. You meant cosine cubed. So make sure you either write it like this. This is why I always put parentheses around my arguments. Okay, I do not like even the way this is written. I would have put parentheses around that x right there because I want to be very clear about what is inside my function and what is not inside my function. All right, so you definitely want to be able to recognize what are composite functions, what they look like, so you know when to use the chain rule and what is not a composite function. All right, so these are just plain functions. They are not composites. 5x to the seventh power. Okay, x is the variable, and there's nothing inside the x. Okay, so that's it. It's just a power of 7 multiplied by a constant. And then sine and cosine, those are just plain functions because they don't have anything inside the sine function or cosine besides a single x. Okay, these are what composite functions look like. Inside the seventh power function is a function. All right, so instead of x to the seventh, it's something to the seventh. Okay, inside the sine function is a 4x instead of just a single x. All right, and then we saw this one up here. Inside the third power function is a cosine of x function. Okay, so these are what we're focusing on today, the composite functions. Okay, so in these problems, we learned how to differentiate those in A, B. Okay, this is one way the chain rule could be written. I do not like this way in particular. You're applying the power rule, so you're multiplying by n. Then you have u to the n minus 1, and then this is the chain rule piece right here. That's the derivative of the inside. All right. I guess Miss Stevenson, who made these notes, wrote it down here, that we're multiplying by the derivative of the inside. Okay, I like the way our calculus book does it better. It has it in function notation. First of all, this is assuming the power rule is part of this, and the power rule does not have to be a part of the chain rule. It could be any two functions inside each other. You could have a trig function inside another trig function, and then the power rule doesn't ever happen at all. Okay, so this is kind of too specific in my opinion. All right, I much prefer this notation down here. So chain rule is like peeling an onion. Okay, so onions are in layers, and you have to peel the outer layer off first, and then you peel the layer in underneath that, and then you get to the layer underneath that and the layer underneath that. Okay, you can also think of it as like a Tootsie Roll. All right, first you take off the wrapper of the Tootsie Roll, then you can eat the candy part of the Tootsie Roll, and then finally you get to that chocolate center of the Tootsie Roll. Okay, so you are peeling back layers, starting with the outside and working your way in. Okay, so when we do the chain rule, we are always going to take the derivative of the outside function first, f prime. We're going to leave the inside part the same because we can't get to it yet. And then we are going to multiply by the derivative of the inside. And again, this could have even more layers, and we just keep on applying that same rule over and over again until we get to the very inside function. All right, find the derivative. Don't leave negative exponents or complex fractions in your answer. Okay, so this problem, we could do it without the chain rule, but you would have to multiply this together 5 times, which would produce an extremely long polynomial, which you would then have to take the derivative of every single term. Okay, that is not a good way to do this. Okay, that's why we need the chain rule for something like this, or especially when we get to like something like letter B, where we have a fraction exponent, then we can't write it all out. I mean, I suppose we could, but we would still have some sort of exponent to deal with. So the chain rule is a very powerful tool, and it's a requirement for being able to do a lot of derivatives. All right, so outside function is the fifth power. So that's the one we do first. So we're applying the power rule, 5 in front, keep the inside the same, and then subtract 1 from the exponent, 4. Then we multiply by the derivative of the inside function. So we just take the derivative, multiply by 3, that's 12, x squared, and then plus 3. And that's really all you can do. All right, there's not a whole lot we can do to simplify this, so we're just going to leave our answer in that form. All right, let's try the next one. So outside function first, so we apply the power rule, 2/3 multiplied in front, keep the inside the same, subtract 1, so that makes this negative 1/3. All right, we're not allowed to leave negative exponents, so we have a little more work to do here. So I'm going to take that whole negative exponent thing, move it to the denominator. Hold on, I forgot to do something. We're doing a lesson on the chain rule, and I almost forgot the chain rule piece of this. So let's not do that. That is a common error. All right, so I'm glad I caught myself before I got too far in the video. Okay, so I did the outside function, but now I have to multiply by the derivative of the inside function. Okay, so the derivative of the inside is 4x cubed. And the plus 2 goes to 0, so it's just 4x cubed. Okay, now we're ready to deal with the negative exponent. So on the numerator, we have a 2, and that's also going to multiply by the 4x cubed. So we get 8x cubed up there. And then on the bottom, we have a 3, and then we're putting this whole thing down on the bottom. X to the 4th plus 2 to the 1/3 power. All right, that's pretty much all you can do. You could rationalize this, but I don't think that's really necessary, and we will just leave our answer in that form like that. All right, next one. So this is one you could apply the quotient rule to, but I would recommend not using the quotient rule because we have a constant on top. Rewrite your original function. -7 times 2x minus 3 to the -2 power. Now we're just doing a chain rule problem. Okay, if you had chosen the quotient rule, you would have still had to do the chain rule. So you'd actually be doing 2 rules in the same problem. If you do it this way, you only have to do 1 rule, the chain rule. Okay, so that's why I recommend this process. All right, so multiply by -2, and you get 14 times 2x minus 3. Subtract 1 from the exponent, so we get -3. Don't forget the chain rule. We have to multiply by the derivative of the inside. Derivative of 2x is 2. All right, we have a negative exponent, so we have to deal with that. The 14 times 2 is going to stay on top. That's 28. Everything else is going to move to the bottom. 2x minus 3 cubed. All right, moving to the back. All right, this one's a little more challenging. Okay, now this one, quotient, I would recommend using the quotient rule. Okay, because if I change this to a negative exponent and move it up, I would still have to do the product rule because I have a function here, not just a constant. So really you're going from either I do the product rule with the chain rule or I do the quotient rule with the chain rule. And I actually think the simplifying process we have to go through at the end is a little easier if you do the quotient rule. So that's why I'm going to do it that way. Okay, so low d high. So low is the cube root of x squared plus 2 multiplied by the derivative of the numerator, which is 5, minus high d low. So high is 5x multiplied by, okay, one thing that might be useful is to rewrite this as x squared plus 2 to the 1/3 power. Okay, so multiply by 1/3, 1/3, leave the inside the same, subtract 1 from the exponent, so you get -2/3. And then don't forget your chain rule, multiply by the derivative of the inside, which is 2x. And all of that is divided by the denominator squared. All right, now we have some simplifying to do. Namely, this negative exponent is a problem. Okay, so I'm going to rewrite this radical I wrote here as an exponent as the 1/3 power. It'll be helpful later. And I'm going to move the 5 to the front. So 5 parentheses x squared plus 2 to the 1/3 power. Okay, so this term, we're going to change it quite a bit. So I'm going to put the negative exponent on the bottom with 3. Then the 5x multiplies by the 1, multiplies by the 2x. So that's going to be 10x squared on top, divided by 3 times x squared plus 2 to the 2/3 power. And all of that is over, multiply the exponents, power to a power rule. X squared plus 2 to the 2/3 power. All right, now we're still not done yet because we now have a complex fraction. Okay, you go back and read the instructions for these sets, for this set of examples. No negative exponents, no complex fractions. All right, so we need to cancel out this denominator right here. So I'm going to multiply the entire numerator by that denominator by 3 times x squared plus 2 to the 2/3 power, which means I have to multiply down here by the same thing. Always multiply top and bottom by the same thing. Okay, so that's going to give us, distribute this all the way over here. 3 times 5 is 15. X squared plus 2. And then when you multiply like bases, you add their exponents together. 1/3 plus 2/3 is 3/3, which is 1. So we actually don't have to write the exponent because it's a 1. So it's just x squared plus 2. All right, that's really nice because it's going to work out really great for simplifying. All right, minus, and then when I distribute it here, it just cancels out with the denominator. So I'm left with minus 10x squared. And then down here, we just multiply them together. So we have that 3, and then x squared plus 2, add the exponents together to the 4/3 power. All right, one more step. 15x squared minus 10x squared is 5x squared. 15 times 2 is 30. 3 times x squared plus 2 to the 4/3 power. Okay, I cannot divide 5 by 3, so it doesn't simplify or reduce any further. So this is our answer. All right, these are the same trig formulas that you've already learned, just written as a chain rule problem. Okay, so it's a derivative with respect to x, but inside the function is a u. Okay, so you do the derivative like normal. Derivative of sine is cosine of u. But then because u is another function, that's what we're saying, then you have to multiply by du over dx. This is the chain rule piece. Okay, when we do implicit differentiation, we are going to do a lot of derivatives just like this. Okay, so you'll see this chain rule in action in this similar way. So this is just, when you see it written like this is the chain rule version of those. All right, so it applies to all 6 of them. Okay, so let's use our trig to do some derivatives here. All right, so these are one function inside another function. So we have derivative of the trig function multiplied by derivative of the angle. So remember, you always start in the outside. So you do derivative of cosine first. Derivative of cosine is negative sine. You keep the inside part the same, and then you multiply by the derivative of the inside, which is 3. So I rewrite my answer as negative 3 sine of 3x. All right, second one. All right, I would encourage you maybe try the next 2 on your own, and then unpause the video and see how you did. All right, letter F is derivative of sine is cosine. Leave the inside part the same. Multiply by the derivative of the inside. And again, I probably rewrite that as 10x in front, cosine of 5x squared. All right, last one, derivative of cosecant is negative cosecant of the inside, cotangent of the inside, multiplied by the derivative of the inside. Okay, I'll probably rewrite that as negative 35x to the 4th, cosecant 7x to the 5th, cotangent 7x to the 5th. All right, next ones. These are probably the hardest ones. So these have 3 layers for the chain rule. Okay, so we first have the power of 4. So it may be helpful to rewrite this as cosine of 5x raised to the 4th power. Okay, over here, secant of 4x cubed plus 5 raised to the 2nd power. Okay, so you always start from the outside and work your way in. So the outside function is the power function. So we use the power rule first. 4 times cosine of 5x to the 3rd power. Then our next layer is the cosine. So now we multiply by the derivative of cosine, negative sine, of 5x. And then the third layer is the 5x, multiplied by the derivative of 5x, which is 5. Okay, so rewriting our answer, 4 times negative 1 times 5 is negative 20. I'm going to rewrite this as cosine cubed of 5x, and then sine of 5x. All right, let's try this one. Give it a try on your own first if you're feeling brave. Unpause the video, see how you did. All right, so power function first. 2 secant of 4x cubed plus 5. That's going to be to the 1st power. So I can put this in parentheses, but I don't really need to because it's to the 1st power. Okay, then multiply by the derivative of secant, which is the next layer. Derivative of secant is secant of 4x cubed plus 5, tangent of 4x cubed plus 5. And then multiply by the derivative of 4x cubed plus 5, which is 12x squared. Clean this up a bit. 12x squared multiplied by 2 is 24x squared. Then I have a secant of 4x cubed plus 5 times another secant of 4x cubed plus 5. So secant squared of 4x cubed plus 5 multiplied by tangent of 4x cubed plus 5. All right, this next one's an example of where the power rule doesn't exist in this problem. Okay, so we just have 2 trig functions. So you just apply that same rule. You start from the outside, work your way in. So start with tangent, outside function. Derivative of tangent is secant squared. Keep the inside part the same, sine x. And then you multiply by the derivative of the inside. Derivative sine x is cosine x. Nothing else we can do there. Yeah, you may be tempted to know that secant is 1 divided by cosine, and then you're multiplying by cosine. You're like, oh, we can cancel a cosine. But see how this has a sine on the inside and this just has an x on the inside? So they are not the same. Even though they're the same trig function, they don't have the same angles on the inside. So you can't cross them out. So that's all you can do. All right, last one is a very AP exam type of question where they really want to test you on the chain rule. So all they do is give you a function notation like this with a bunch of values. Okay, this forces you to know the chain rule, okay, because you have to know how to apply. They want you to find h prime of 3. So h prime of 3 is equal to, and you got to know how to apply the chain rule. You do f prime first, keep the g on the inside the same, and I'm going to go ahead and plug in my 3 instead of x, and then you're going to multiply by g prime of 3. Okay, so now we're going to start grabbing numbers from our list of values up here. So we have f prime of, and then g of 3, hopefully they told us up here, there it is 4. And then g prime of 3, they told us that right there is negative 5. Okay, I have one more value I need to grab. I need to know f prime of 4. Right there is 8. So I have 8 multiplied by negative 5. So my answer is negative 40. All right, hope you enjoyed the video on the chain rule. I will see you on the next one.